Hi people, this is a tutorial from chapter 9 of the textbook Mechanism Design and Animation. It deals with the simulation of a planetary gear, or more specifically what is called epicyclic gear. And in that particular problem, I did this thing in class for the case where the ring gear was fixed. So what I would like to do today in this video segment is deal with the case where the sun gear is fixed. And notice that if that is the case, you're in the overdrive mode and the gear ratio is 0.71. We'll talk about this thing later on, and in fact verify these things through the Catia simulation. I'm assuming that the sun has 30 teeth, and the ring has 72 teeth. And since the number of teeth are proportional to the radius of the particular gear, I'm going to assume that the sun has a radius 3 inches, and the ring has a radius of 7.2 inches. Okay. Here's the situation. It is made. This thing is made of a ring, which is the yellow one, a sun that is the green one. The planet is this orangish, and the carrier is right here, this long rod, and there's a shaft in the back that is sitting stationary. These are very simple parts to make. However, I think it's still worth giving it a shot, and it's going to take me about maybe 5-10 minutes to make these parts. And once we make it, then it's easy to put it together. So I'm going to close this thing, insert, so file, part, new, product. All right, let's insert a new part in there. And let's start with the sun. Okay, so I'm going to rename this thing to be the sun. Sun and sun. Okay, let's make this on this vertical plane. I'm going to sketch a circle of radius 3 inches. Let's change this into radius 3 inches. Okay, and exit. Oh, I'm going to make a little hole here, a little circle here, which eventually turns into a hole, because we want to plot the angular velocity, and we need to create sensors. Therefore, I need some identifiers here. So anyway, so there we are. Exit and pad it by. Okay, we've got to go to wireframe to part design, and then pad it by. Let's make them all 0.5 inches. 0.5 inches. Okay, there's the sun. All right, let me also change the color to yellow. Actually, I think in the original thing that I showed you, I made it green. So let me make it green. Okay, good. Now insert. Let's make the ring next. Insert new part. Let's do it like that. Insert a new part, and let's call this thing the ring. So right click, properties, ring and ring, ring and ring. So this is going to be something that has a radius 7.2 inches. So let's make it on this same plane, vertical plane. I will sketch, zoom out, a circle which is radius 7.2 inches. 7.2 inches. And since we wanted to have a three-dimensional, aspect to it. I'm going to make a little ring outside and put a marker here because we're going to plot angular velocities later on. There we are. Let me see now. I didn't really want this thing to be tangent, so let me. No, it's not tangent. Okay. Alright. So exit and pad it 0.5 inches. Okay, there we are. Alright, it's very close to that border. That's irrelevant. Actually, you know what? Let me go ahead and clean this up. So let me go to this pad, this sketch. I want to delete that tangency and then make this thing smaller so that we don't have some issues later on. Alright, good. Let's make this thing, I think I made it yellow. Alright, now let's make the planet. So go there, insert, new part, and we make this thing the planet. Right click, properties, planet, and planet. Planet. Let's make it. Double click on a convenient plane, on that vertical plane of the sketch. There we are. A circle, and then we're going to make a tangent to both. Okay. There we are. So we make this, control that. Where's that? Tangent to each other. And this and that guy also tangent to each other. Sorry. Let's see now. This, control this, tangent to each other. Alright, and let's make a little circle here so that you can see the rotation of these things later on. Alright, so pad it 0.5, and if I'm not mistaken, I made this thing orange. Colors don't matter, but I want to be consistent with what I showed you before. Alright, let's do the shaft. The shaft is sitting in the back. Okay, so insert, new part in there. Let me call it the shaft. Properties, shaft, and shaft. And let's make it on that back plane. I will sketch a little circle. There we are. Exit. Okay, and then pad it. Let me see this back plate. Okay, there we are. Okay, that's. Oh, sorry. Let's flip. Let me flip this thing. There we are. This is a shaft. Okay. Okay. Now finally the carrier. So double click, insert, new part in there, and let me call it the carrier. Properties, carrier, and carrier. I think carrier has 2 R's. Okay, that's good. So let's make it. Now on that front face, I will sketch. Okay, something that looks like that shape that I had in my original drawing. I'll clean it up in a minute. Okay, so let's go here. Okay, let's first of all make sure that this line and that line is symmetric with respect to this. I think it is, but anyway, so shift it a little bit. Let's make sure that this control that these are concentric. Alright, and the same thing down here. This guy control that guy, make it concentric. Some of these are not necessary, however, I would like to follow. Alright, so there's the carrier, and I will actually make a little indentation here, a circle here, which eventually will turn into a hole once I pad it. So pad it, 0.5. There we are. And this thing, I believe I made it, if I'm not mistaken, that color. Now something I forgot to do, and I'm going to do that right now, is I would like to create a point at the center of each of these circles, because we're going to be creating sensors and then plotting the angular velocity, for example, at some point. At that point, we're going to make it easy to make it the center of these. So let's go to the, for example, this is the planet. Double click on it. You're there. Make a point. And the method of making the point is going to be circle center. Right there, and there is the point. So a point has been made right there. You can see that. And then I'm going to do one in the carrier. Double click on the carrier so that I go into the carrier part. And I don't know why did this thing double. First of all, let's make the size of this 0.5. That's good. Okay, fine. I don't know why it became okay. Let me make this thing 0.25 actually. But that was not the issue. I want to make a hole right there. So a point at the center of that circle. That circle is made. You can see that there's an X there. And now we're going to go to the ring. Double click on the ring. There we are. And make a point at the center of that circle. Whoa. Let's try it again. The center of that circle. I think I have to zoom in. There. There. The point is made. And finally, I'm going to go to the ring. Double click on the ring. Let me hide this. And make a, are we in the ring? I think we are. Make a point at the center of, let's see, cancel. Okay, zoom in. A point, center of this. All right. Okay. So all the parts are made. However, I'm not going to create assembly constraints. I will go and create all the joints directly in the digital markup. Maybe a good idea to save this thing. I'm not sure. Just leave it the way it is. So we go to the digital markup, DMU kinematics. And okay, so first I'm going to anchor the shaft. So new mechanism 1, anchor the shaft. Okay, then because because the sun is fixed, I create a rigid joint between the shaft and the sun. Shaft is stationary, so the sun is stationary. Let's create some revolute joints. Revolute between the axis, between the carrier and the sun. Okay, or not the sun, the carrier and the gear. So axis and axis, and then plane of the shaft and plane of the gear. But there's an offset because the planes that I'm taking, they have offsets in it. Okay, let's do another one, another revolute between the carrier and the sun, for example. Oh, it really doesn't matter, or the shaft, because it's going to both stationary. So another revolute between the axis of the carrier and the axis of the sun, plane of the carrier, plane of the sun, and there is an offset involved. Okay. One between the carrier and the planet, revolute between the axis of the carrier, axis of the planet, plane of the carrier, plane of the planet, and there is an offset there. Okay, now my strategy is, instead of making gear joints, I'm going to make roll curve joints. So roll curve between this arc, this circle, and the circle of the ring, and another roll curve between the perimeter of the planet and the perimeter of the sun, and we say okay. Now if you check your let's check these things, check our joints. There should be 3 revolutes, 2 roll curve, and 1 rigid. And degree of freedom should be 1, unless I made a mistake somewhere. Yeah, degree of freedom is 1. You can see that there is 1 rigid, 3 revolutes, 2 roll curve. Now, since our gear is, our ring is the input, so I'm going to make the revolute joint between the ring and the shaft as angle driven. So let's see now, where is this shaft and the ring? Right here. We're going to make this thing angle driven, 0 to 360. We say obviously the mechanism can be simulated, and you can do that manually, and you see that everything works. This is fine. Now we have to put some physics into this. The first thing I'm going to do is to create some sensors here before I put the physics into it. And the sensor is here, the ball rolling down a ramp right there. It's been an acceleration sensor. The first one I'm going to make is going to be the sun. Obviously the sun is stationary, so the angular velocity of it is going to be 0. We know that. And the reference product is going to be the shaft that's stationary, and the point is going to be that point which sits on the, right there, I can selecting it on the sun. Okay, good. Let's make another one, another sensor. Let's call this thing carrier, and the reference product is in the shaft, and the point is the point on the carrier, which is right there. Do another one. This one is the ring, by the way, which is our input. The input is going to, or the reference product is going to be the shaft, and the point is going to be the point on the ring, which is right there. And finally, it is the, which one is it? The planet. Okay, so another sensor. This is going to be the planet. And reference product is the shaft, and the point is going to be the point on the planet, which is right up there. Okay, let's put some physics into the problem. Click on f of x, click on the mechanism so that you get the command associated with the mechanism right here. The formula, let's assume that the ring turns at 60 RPM, which is 360 degrees per second. So 360 EEG times, or let's say divided by 1s, 360 degrees per second, times the time. Alright, and let's do the simulation with law, right there, simulation with law. Activate the sensor, and everything that we want is angular velocity. So let's see now, sun's angular velocity, which is our angular speed, right there. You select this thing, that turns into a yes. Scroll down, carrier angular speed, select that, that turns into a yes. Scroll down, ring angular speed, and finally the planet angular speed. Okay, move this thing down, get it out of the way. Let's do a simulation for maybe a 3-4 second interval. make it 4 seconds. And I don't have to go that, well, I'll change this into 80. I mean, the bigger this number is, the longer it's going to take. So, okay, so let's play it. After the 4 second expires, this thing stops, and we're going to say graph. All right. So what we're getting here is, let me zoom out of this so that we have more room to display these things. Okay, a little bit more. Okay, so we have 4 curves. Let's look at the one which says sun angular speed. Sun is stationary. You click on it. Notice that the yellow curve corresponds to the sun angular speed, RPM, as you can see, and of course it's 0. Let's do the ring angular speed. Needless to say, that's the red one, and the scale is red, 60 RPM. That was our input. So if you look at the carrier, carrier is the green one, and it shows you that it is around 42. In fact, if you put the cursor on it, right underneath in this white area, you see the actual value, which is 42.7, something like that. Okay. And if you select the planet and you put the cursor on the blue one, it says it's around 102 RPM. How do these match with our calculations? Okay, so here's the situation. The ring RPM was 60. Number of gear teeth on the sun is 30. On the ring is 72. So the gear ratio, according to the table that I showed you at the beginning, is 0.706. So if you take the 60 RPM, the input, multiply it by gear ratio, you get 42.3, which is very close to what Catia gave us. Now, what is that 102? Where is that 102 coming from? Keep in mind that the planet not only rotates through the rotation of the sun, but it also spins about its own axis. So this thing is actually this 42 is the spinning angular velocity, but it also goes around the axis of the shaft at basically you add the 60 to it because it goes around at the 60 RPM because attached, it's going with the ring. So 60 plus 42 is about 102. So it agrees with what Catia gives us, and that completes the tutorial. Have fun.